Thank you so much. I guess it's probably a little unusual for your speakers to come 4 full days earlier, but I'm so glad that I did. It's been so nice meeting with so many of you, to see both campuses, to have all these great lunches with students. It's really been a pleasure. I'm taken with the just sheer breadth of things that you guys work on here. It's really been amazing. So thank you for taking the time to meet with me this week. And thank you so much to Mark and Nicola and Peter and Damien for really taking care of me all week. So today I'm going to be talking about just kind of like a little highlight reel of some of the things that we're working on in the lab. So this is, I'm the PI of the Rock and Ice Mechanics Lab. We got a big team. Some of the data I'll be showing you are data points that I've collected way back when, but a good number of them are collected by members of my team, many of whom are here, and one of them is over here. So the Rock Mechanics Lab at Lamont was started way back in 1968 by Chris Scholes. It was one of the many birthplaces of what we know about fault mechanics and earthquake physics. I came in 2011 to do a postdoc with Heather Savage, who took it over after Chris. And since that time, Heather's left, and we moved to another building, and we've been little by little adding ice to the program. And then just at some point, I just kind of slid in, like it's now called the Rock and Ice Mechanics Lab. So that just happened. But it's really fun. Our big team works on a variety of projects, both rock and ice. And I think the common factor, though, is that we think about, you got a chunk of stuff, it experiences some kind of stress, how does it respond? And so I like to show this figure to just kind of bring home that ice is a rock, is an ice, it's all the same, and on so many various levels, there are similarities that we can explore. So, as I said, we're working on a big variety. I can't talk about all of these things today, but it supports a nice team, and in particular, it means we can diversify our funding, which in today's world is a really good thing. So when we think about rock and ice, I always like to start with this kind of thought, that you might think like, oh, they're just so different. How can you possibly compare these apples to oranges? Well, the way you can compare is by thinking of them and how they behave relative to their melting temperature. And if you put those on the same scale, this homologous temperature scale, then you can start to see big trends. Like, so, things in this range, less than half of their melting temperature, are going to have a brittle response versus a ductile response. And you see that that there's lots of overlaps. Does this work too? There. Good. There's lots of overlaps with what people are doing in high temperature rock rheology and low temperature, crustal friction rheology. And one thing to point out too is that usually, not always, but usually, these are different labs. Like one lab, because of the differences in these temperature ranges, like one lab will focus on sort of crustal, brittle processes. Another lab might focus on high temperature in olivine. But thanks to our handy liquid nitrogen, which can get us a nice cool range, and only having to traverse about 200 degrees in our lab with the same rig, we can explore the whole vast brittle to ductile world. And fortuitously or coincidentally, with this liquid nitrogen cooling, this also happens to be the temperature range of many icy moons of the outer solar system. So even though I'm going to be kind of just talking about the properties of ice, it's enjoyable to put it in some sort of context, some kind of motivation to study the rheology. And so we're thinking about icy moons, in particular ocean worlds, where the surface temperatures are quite cold. There's variations, but say on average of maybe like 100 K, down to, by definition, if they're in contact with their liquid ocean, melting temperature, right? And so this could be a couple hundred degrees. And as such, we see that they could be like Earth, having these kind of brittle to ductile transitions that we think about, these little Christmas tree diagrams. And so, also to kind of put a context or something that will lead us through, is thinking about heat. And I'm not someone who models heat generation or comes up with these big models, but those who do say that in order to get global liquid oceans at these very, very cold temperatures of the outer solar system, there's a combination of a variety of mechanisms that make heat. So I provide all of them because in particular radiogenic heating is of course very important, as are impacts for getting localized heat on the surface, but I don't actually study those two. So I'm actually going to focus on the middle two, frictional heating, which you might have localized in the crust, the brittle portion, and tidal dissipation is the process we'll talk about in the more viscous part. To guide how I'm going to lead you through this, I'm going to start with friction, kind of give you like an idea of how we run those experiments and give you some data on pure ice results that we've measured, but then tell you about melt. What happens when you've gotten heat and you've generated this small distributed partial melt? How does that then affect the mechanical behavior? And finally, I'm going to wrap up with some exciting, ongoing, right now, they're being conducted, they probably just ran experiments today, some of those results, or some of those works, those projects that I want to tell you about. But we're going to start off talking about ice, how we make it, and all of that. But to start with, this is the first question people ask me all the time. Which ice? Are you going to make those high pressure polymorphs? Sorry, no. Well, I'm just going to be focusing on hexagonal ice. There are labs that use, confining pressure, a confining gas to work on ices 2 and 3. There are folks who will use diamond anvil cells to get to super high pressures to work on some of these high pressure polymorphs. And that's important that people are doing that because some of these large moons, which they think have a really large liquid layer, H2O layer, and are, with depth and having the larger gravitation, they think that they are experiencing high pressure and probably have these high pressure ices. However, my two favorite moons are these two little guys, and they are of a size that they are not experiencing those kinds of high pressures, and it's estimated that they just have regular old hexagonal ice, which is great. So that's what we're going to be focusing on. And our kind of little niche, since others are working on high pressure systems, our sort of niche in the world in our lab, where we're kind of trying to be at the forefront, is thinking about impurities. So the various missions that have gone out have identified with infrared spectroscopy that there's more than just ice, pure ice on these moons. There's various kinds of hydrated salts. No one salt is a perfect match to the spectra, so there's a kind of a laundry list of possible ones. And our lab has been spending time thinking about some of these different systems and how having that the second phase could reduce melting temperatures and create partial melt. And we see things that look like volcanism and impurities on the surface and stuff. So that kind of motivates why we're looking at this. How do we make it? Well, we get all bundled up, a little bit like you guys all are today in this room. But we get bundled up and we get in our walk-in freezer, and we make a multi-step process of coming up with these controlled samples. And we're following in the footsteps of David Cole from Krell, who developed this practice so that across the spectrum, lab to lab, we can all follow this method and compare our results. And so we make some seed ice in a bucket. We then grind it up with a food processor, sieve it, pack it into a die, pull a vacuum on that die, and then introduce, in the case of these pure ice samples, distilled water. We then freeze it on a cold plate. And so what we get is really uniform, kind of like foam texture ice, very low porosity, uniform grain size top to bottom, sample 1 through sample 100. Like, we're pretty confident with this. And to now add the partial melt, we do all those same first steps, pull the vacuum, but instead of liquid water, we add the solution at that stage. And then what we get is pure ice grains, and then this distributed melt phase throughout. And what is the structure of that melt phase? Well, that is dictated by surface energies, so relative solid-solid surface energies and solid-liquid energies. And you can kind of characterize this with this property called the dihedral angle. And this dihedral angle is important because for samples with materials with less than 60, it's considered that the melt is fully mobile. It's in these triple junctions, and it can like communicate through like tubules. Whereas if it's over 60, it could get trapped as like blebs, which probably wouldn't have any transport capabilities and might not really affect the mechanical behavior. And if you don't believe the little cartoon here of what this three-dimensional network might be like, hope you believe this image taken by Jane Blackford, where she took a ice plus saline, which is very similar to what we've made, and put it in the SEM, quenched it. So like liquid nitrogen quenched the saline. And then the SEM, the ice, which is this sort of gray mottled stuff, like it sublimated faster than the quenched melt. And so you could see that really crazy looking network there. And so this is incidentally, this less than 60 degrees angle has been determined in every binary system that I've ever looked at, and I've been trying to kind of make my way through all the different systems. I'm sorry, not every binary system, every binary with ice system. So various salts and acids have this low dihedral angle, which, by the way, is similar to what you have for olivine plus melt. So again, making our work relevant and crosstalk between the different worlds. And so since this is supposed to be a mechanical control, our view of the world is that we can use one system, and it's analogous to other systems that have this same kind of microstructure. Okay, so let's start with frictional heating friction experiments. How do we run a friction experiment? So we have a cryogenic biaxial apparatus that is very similar to what Damien's lab has, Chaz's lab has. Essentially, you got to squeeze two pieces together and slide them past one another, right? So ours is a double direct shear, which in the horizontal direction squeezes our 3 blocks together. And then we use the vertical piston to slide the central block past. So we're measuring the normal stress that we're applying and the shear stress, which is, the shear stress of these two interfaces, but we're measuring with a load cell that's up here, where friction is shear divided by normal. Okay, so we've been working on friction in the lab using that biaxial apparatus for a while now, and we've been kind of exploring various parameter space depending on the thing that we're thinking about. I started off thinking about glaciers, and so we were working at relatively warm temperatures, kind of minus 20 to almost 0. So looking at temperature and velocity dependence with ice sliding on rock. And then we started doing sinusoids of that forcing, thinking about some of these tidewater glaciers that are kind of moving with the tide. They're modulated by the tides. Some people were like, wait a minute, but this ice isn't like sliding on rock all the time, it's sliding on tills. So a postdoc came, Seth Saltiel, and he made advances on the apparatus and added a nice till layer. So he was looking at that. We're also contemplating what's happening at the asperities, how they change with time, and we're looking at normal stress effects instead of just the constant that we usually run. And in all these cases, we do everything kind of through this framework of rate and state friction. I see people cringing, I know. Don't worry, I am not going to go delve deep into rate and state friction, particularly because there are people in this room that know it actually far better than I do. Ooh, and some of my equations got all wonky too. Maybe that's the reason we're all squinting. But okay, they got a little wonky, but there's a velocity dependence and a state dependence to friction, and The thing that I wanted to focus on, though, is the stability, which is determined by this A minus B property. The way we measure that is that we run an experiment where we're sliding at some constant velocity, and then we do a bump up to a higher velocity. So this velocity step happens. What's the response of the system? Well, it'll be going at a constant steady state friction, and then it will have this immediate direct effect. It'll jump up. But then the system, the friction, will evolve to a new frictional value. And will that be lower than the first value or higher, determines this A minus B. And this is important, and the reason people care about this, because this tells you whether your system is just going to creep stably, or it might have an earthquake or a stick slip. And so this is kind of an important property. And just to kind of give you more of a tactile feeling for what stability is, or what a stick slip earthquake might look like, is that if you imagine this block that sort of stays there, and we're pulling the circle off to the side, but it hasn't moved, the stress, or friction, if we're measuring that, will increase, and then it will plummet when it finally moves forward. And this can happen over and over again, and it has this sort of saw-like manifestation. Okay, so let's look. That's all the background. Let's look at a study that Mai conducted for his first few years at Lamont, and it was motivated by icy moons. In particular, he's thinking about Enceladus, is the moon that has these tiger stripes on the bottom, these 4 gigantic faults from which emanate these huge plumes of material. And so he used the biax to do, again, these double direct shear experiments, and he went all the way from 100K down to, he didn't go all the way to 73, a little higher than that. But, various cooling systems were used, and then to get the really cold temperatures, it was just like straight LN, creating kind of its own weather system in the lab. But he got really great data. And so I won't go into details. You can definitely check out his paper. But just kind of a highlight, here's a sampling of 2 different cases that he saw. And so here's what we drove the program, this velocity step. And we see at relatively warm temperatures, 250K, is kind of like that cartoon classic thing that I just showed you, where you get a velocity step that evolves to a new value. But at the colder temperatures, you can see this classic stick slipping. And it was audible as well. You could hear click, 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 click. And with velocity, there was a different periodicity, or blanking on the word for this, but a time between events. So he looked at temperatures the whole range, and if you plot those in this way, with cold on the top, like the top of the shell might be, he got a response that was very exciting to me. So in rock mechanics, in Earth studies, it's way back in the 90s, was identified where the A minus B is negative for rocks, coincides with the source of a lot of earthquakes. This isn't every location, every instance, but there's this apparent seismogenic zone related to the mechanical properties of rock. And at least as a function of temperature, again, we haven't done this at all the normal stresses to really put this as depth, but temperature is the largest forcing on these icy shells, and we're seeing that same response, which we thought was pretty exciting, because that gives the possibility of a seismogenic zone on these icy moons. So if you are building a mission and you want to place a seismogram on top of an icy moon, it's nice to know that at least this is possible, that you might have some events. So that's pretty exciting. But I wanted to tell you about how melt affects things. So based on that motivation of thinking about Enceladus, where its plumes were ejecting liquid water and a whole lot of other species, one of the things that was in this sampled in the geysers was ammonia. Ammonia is interesting because it has a very deep eutectic, meaning this has this antifreeze effect of about 100 degrees. And so if that was the case, then you could have melting in an icy shell, much higher up in the shell than like way down at the ocean interface. And so he looked at the friction of both icy samples in blue and ice plus ammonia samples. And the freezing temperature is like 175. So here, let's see. So on this side of things, this is actually solid. And we still see a reduction in friction from the pure ice stage. But then we also see, continued reduction of friction for where it is a partial melt phase. But we don't see a total plummet of the friction. Like we're still pretty high up here. And I think that's important too. So it's not the case that you create melt and now you'd lubricate your surface and friction would plummet, frictional heating would plummet. That's not the case. It seems that having this distributed partial melt, it reduces the friction, but you still have a lot of solid contacts that are, maintaining the friction, and therefore you'd be able to maintain frictional heating. So he does an analysis in his paper about frictional heating, and he has submitted a paper that the forcing is periodic, so matching the tide. So please look at that if you get a chance. But one final thing, how did having the melt phase affect that stability or that seismogenic zone? Well, this is an interesting effect. If you look at, so this is the melting line, and so it's partial melt below this, but solid above this. And the shape of this is almost identical to the pure ice case. But at partial melting temperatures, it seems to go kind of very far extreme in stabilities in both cases. I don't know exactly what the reasoning for that, but I think it's a pretty interesting result, and maybe can be scaled up for these icy moons. Okay. So that's friction. But I'm going to move on to the next potential heat generating mechanism, which is tidal dissipation. So what is tidal dissipation? So when these icy moons are orbiting their parent bodies, and this is not at all to scale, Jupiter's enormous relative to these little moons, they're trapped in a kind of resonance, which keeps them in this very eccentric orbit. And with that, the tidal bulge kind of moves in position. The overall effect on these icy moons is like it's sort of torquing the icy shell. That creates heat. And you think, how does that create heat? Well, you see my little picture. If you haven't, I say go home today and do this. If you've ever taken like a coat hanger or a paper clip and you've moved it back and forth, and you feel it, it's hot. What's happened? You've turned your mechanical energy into heat by moving little defects back and forth inside of this material, creating frictional heating. So how do we measure this in the lab, though? So we take an apparatus. Some studies have done this way, torsional, but I've always been involved in this direction, which is you apply a uniaxial stress, a sinusoid of stress, to the sample, really small. We call it tickling. Really small stress, and then you measure the strain, which is also periodic. And if they were exactly in phase, that would be a perfectly elastic material, which doesn't exist. All real materials have some phase lag. The bigger the lag, the more squishy, attenuating the material. Forgive my little equations got messed up, but we can also measure the modulus. In particular, it's called the relaxed modulus, and that comes from the amplitude of these two waves, the ratio of the amplitude of the stress and the strain. All right, so we do this in the lab, the widest frequency range we can possibly muster. For us, it's been about 10 hertz down to the 10 to the minus 4 hertz. And this is a cartoon of the general shape of these curves. So we have the modulus at the highest frequencies, like if you shot ultrasonic waves through something, the values you would get for modulus are pretty close to the theoretical unrelaxed modulus. But with frequency, this weakens. In the same way, like the inverse response is the attenuation, which we denote with this Q. And again, I don't actually model the heat, but this is what is used. Attenuation is what's used to figure out the energy dissipated versus the energy stored in a system. So focusing on the bottom part, that curve can shift with things like grain size or temperature or just material properties, and so that's what we measure in the lab. In particular, in this whole range of the yellow, which is the anelastic response, which is time-dependent but fully recoverable. And this, our motivation sometimes in the past has been to think about seismic waves, how seismic waves are damped. But it's the same thing, just at lower frequencies for thinking about tidal deformation. So, same mechanisms hold true. So a study that I'm very proud about, it's very old, sorry, but I have to show it, is that I went to Japan. I was working on this novel material called borneol. It's just like mothballs, essentially, but it's really nice to work with in terms of like it has diffusion creep and dislocation creep, and you can really control the grain size and the temperature range. Again, that homologous temperature we talked about is very easy to obtain in the lab. And we got really beautiful data. It's the black data in the back that you can barely see. And we were looking at a variety of temperatures and grain sizes, and we figured out how that scaled to each other. And so then we started taking all of the other data sets of olivine, single crystals, large crystals, mixed rocks, and we figured out if we scale them by, the Maxwell frequency, which is the modulus, the unrelaxed modulus, divided by the viscosity. Sorry, that's got a little wonky, but the viscosity, which is the Maxwell frequency, all of these various data sets collapse to the same curve. This is fun. This is a universal response for materials that are kind of pristine, as fabricated, tested in a very low stress environment. The consensus in the community is this mechanism. They all plot on the same, which means it's the same mechanism. And the consensus is that this is called diffusionally accommodated grain boundary sliding. What's that? So if you imagine all these grains in a sample and you start to, whether it's shear it or deform it, the grains want to move relative to each other. The first step, it's just elastic bonds, just kind of stretch and let it. And then the grains are going to have to start moving relative to one another. They're going to get caught up on each other and start to build little stress concentrations, which the system wants to relieve by diffusion at the grain boundaries, moving little diffusion. So in the anelastic regime where it's seismic to tidal, that keeps happening over and over again. Things moving back and forth in a non-permanent way. At longer time scales, things actually move over. You can't get them back. They're sort of stuck in an energy well, and that's permanent deformation. So our measurements in the lab, we're trying to focus in this area. So I just showed you my 2011 work, so that's kind of old news, but we got new news. And that is in our lab now here in Lamont, we've built a new apparatus that is based on the really nice high-resolution one we used in Japan. Postdoc Hatsuki Yamauchi came, and it's the apparatus that both she and I have used. And so she built this, adapting it for low-temperature work. A lot of nice elements to it in that it uses lasers for displacements. You can really get high resolution for your strain. And the stress is applied by a piezoelectric. You just get really nice quality data. And in doing so, she tested as fabricated ice samples at very low background stresses, and she was able to match this master curve, which I think is like the first time we've been able to do that, and it fits. So we can have that same like very low stress diffusion at the grain boundary process. But that's not why we built it, though. We actually wanted to go to the next level to start looking at other effects. So stay tuned. She's done some really nice experiments, both increasing the strain, which adds up dislocations in the material, and then taking it to a full extreme. We got Priestley Glacier samples, natural samples, that have a really strong fabric, and they had a quite different response that doesn't scale to this, which tells you there's more mechanisms when you have a fabric. There's more mechanisms of heat that go of generating heat beyond just the little grain boundary processes. Now, I promised you we'd talk about melt. Our goal is to also look at melt in samples with this apparatus. We haven't done that yet. But I did study this, as Mark alluded to, when I was in Japan. And so this is, again, this organic material. But again, my knowledge of, or my intuition, I guess, about how materials with similar dihedral angles should behave, I think we'll probably get a similar response. And that is that as you increase melt, you get an increase in attenuation. And why is that? Well, that same mechanism of trying to get the stress, relieve the stress at concentrations, that diffusion around the grain boundaries, well, if they don't have to take this long path, if they can actually take a superhighway through the melt, it actually makes the whole system or the whole process a little faster. And so the idea is that, with increased melt, this grain boundary process is sped up. But it also affects both modulus and viscosity in the same way, so then you do that same normalization, it collapses to that master curve again, which is nice. However, after I left in 2011, they realized that us comparing our melt samples with this pure Borneol, which was actually measured at 60% of melting, is kind of not a fair comparison. What happens as you approach melting? Well, I'm going to present this effect called pre-melting. And so here's where that black data from the previous slide was. Down here, it's a very low homologous temperature. They systematically increased it to approach melting, and they saw this gradual increase in the attenuation. So what's that all about? So the same thing I just said about the superhighway of melt creating fast diffusion, it also happens before melting. So what is pre-melting? Well, you may have seen in other materials too, that from about 95% of melting to melting, there's this a different relationship with temperature, different activation energies. And the idea is that you start to get into this philosophy question about what is melt? What is a grain boundary? It's disorder, right? And so if you've got this tight crystalline material right next to each other, the hotter the temperature, these atoms start breaking apart, and you've got this disorder in the grain boundary. It's not true melt yet, but it's this increase in disorder that increases and increases as you approach melting, and that disorder seems to facilitate diffusion when it's experiencing a periodic stress. Okay, so again, this is Borneol. I kind of went to the side. We haven't observed this yet in ice, but I've got a proposal in, fingers crossed. We'll see. All right. Now, in my remaining time, I don't see a clock anywhere, but in my remaining time, I just want to highlight some of the current projects that are happening in the lab. In particular, this is a pretty exciting thing. I've had calls before where people say, Christine, what's the viscosity of ice at melting temperature? It's it's a range of 16 orders of magnitude, right? Because it's got to pass through this whole range. Pure ice all the way down to a pure water where it's 10 to the minus 3 Pascal seconds versus 10 to the 13. But in fact, we don't have a curve that describes all this. Folks in looking at rock, at molten rock, have this is a compilation of numerous studies, have looked at this, and they've described that basically you have this this decrease with melt fraction that starts here, and then there's a kind of precipitous drop in viscosity, which happens at this critical melt fraction. So what is that? That's just basically when it stops being all solid, and now the solids aren't controlling the framework, but the melt is. So where does that transition happen? In these studies, Costa noted that it seems to depend on a lot of things, like the strain rate, crystal shape, size, viscous heating, things like that. So our goal is to come up with this for ice. It's not super easy because you can't do it with one machine. You got to go kind of in two directions, right? Because there's two different types of experiment. Over here, we can do this with that pink apparatus that we were going to use for attenuation, and she has in fact started those experiments. And then to come from this side, we need a different kind. It's a rheometer. So it measures the resistance, the torque needed to spin a little bob in a cup. And so we calibrated it with like motor oil and silicon oil and things like that, and it'll get us through slurries on this side. Just as an aside, our plan of attack is kind of twofold, where you can control partial melt by either staying at a constant temperature and then just like little by little adding more salt in each sample, or you can do it by a single composition and then just changing your temperature, and then by your lever rule you'll be changing the fraction of melt. This is more like what a moon would be feeling, right? Where it has a certain dilute composition and there'll be a temperature variation in the shell. However, maybe we'd be confused by the temperature effect on the ice as opposed to like the system effect. So we're gonna attack it in both ways, and that's what she's been working on. Where just a little bit more about the rheometer. It's bought off the shelf, but we did our own custom cooling system. And yeah, there's always a little balance in wanting to toot the horn of your student or your postdoc without like stealing their thunder and sharing their actual data. So without showing any of her real data, I want to just say that she's collecting gorgeous data. And the only previous study on ice plus saline was this one from 1999, where they found this distinct softening, this is strain rate, when you had 7% melt. Well, she is looking at less melt, quite a bit more melt, and the curves are fitting beautiful with the previous data. And so she is well on her way. Again, with this sort of two mechanism little pivot in it. It's looking really nice, and she'll be able to take from all these different melt fraction samples, she's going to go back over to this plot and start coming up with this linear relationship, which we refer to as alpha. She's even started seeing a drop-off, which you relate to that critical melt fraction. So stay tuned. Yeah, I think within the next 6 months she'll get that out, followed by the experiments going in this direction. So hopefully we'll be able to provide this viscosity relationship over the whole parameter space, which maybe doesn't sound like much, but I think people that are like modeling these dynamic systems, I think are hoping for something like that. Okay. Another study that we're working on, Cassandra Seltzer, she's an NSF postdoc fellow who came to our lab just less than a year ago, and she wants to study if you like really shear an ice partial melt system, will it form a fabric, and in particular, will the melt form a distinct fabric in a really highly sheared sample? But before she does that, I was kind of asking, like, well, what do we know about grain growth? Like, you want to know what you started with, and then like what would have evolved just by it sitting in the experiment, and what evolved because you what it did because you strained it. And so we were looking through the literature, and we're actually really unsatisfied with the literature on how melt affects grain growth. And so she actually had two undergrad interns this summer, and she had this very strict freezing, annealing, quenching time scale schedule for them. And they did a great job, and in just a couple weeks, or a few weeks over the summer, she's able to get this really nice study where you don't need computer methods to tell you that over 300 hours these grains grew, right? You can see it with the naked eye. And so it was nice for the undergrads to have like a tactile visual response. And she was able to take those values and plug it into the kind of standard known grain growth law and determine these values, P and K. And I don't just cut to the chase. Here the bottom curves are the pure ice samples. the cut to the chase is that with a little bit of saline, melted saline in the grain boundaries, they become much more mobile. The grain boundaries move, and you can grow your grains much faster. But too much of a good thing can slow it down. So if you get to a higher concentration, she actually saw a decrease. So the orange has more saline than the purple at the two temperatures she looked at. So it seems like a little bit helps, but then then the salt just kind of gets in the way. And finally, the very last thing I wanted to talk about is why we're here actually this week, is that Mahi has been running experiments. He finished his friction experiments and he moved on to this, where he's trying to figure out, if he has created melt, what is the fate of that melt? Can it be mobile in an ice system? So he's using a pressure cell here that has steel walls so it can't get fat, and he's squeezing it at different applied stresses. There are porous frits on either side, which are open to the atmosphere. So it means that the ice feels the high stress, but the liquid can feel the atmosphere, basically. He applies the stress, and he watches it shorten, and the melt, kind of like a French press or a sponge, it basically gets squeezed out the two ends in a nice controlled manner over about a 6-day process. He's got a couple ways that he can monitor it. One is that there's an LVDT that's actually measuring the shortening over time. He also can weigh the frits before, when they're bone dry, versus after, when they're soaking wet with all this saline. Also, a last method we use, which we love, is that we can also take a little chunk, a representative chunk of the sample, and melt it down and put in a refractive index meter, which tells us sort of the degree of saltiness, which we've calibrated. And he's found that, if his samples start here, they end way down. I don't think down to 0, but very low, very low. So the reason we're here is kind of making sense of these curves. So how your shortening changes is a function of this evolving system where the melt is leaving. And these are similar experiments, not identical, but very similar to what Tim is going to be running. And so we're kind of sharing notes, and these guys are helping us figure out what to do with the data and how to make sense of this. And it's been a really great week. I'm looking forward to more collaboration. And thank you so much for listening.